All right, let's dive in. Today, we're going to explore a really fascinating family of chemical compounds. And trust me, they are all around us, from our medicine cabinets to our cars. Let's get to know the alcohols, phenols, and ethers.
So, to get us started, here's a little riddle for you. Think about a glass of wine, an antiseptic you'd spray on a cut, and one of those old-timey anesthetics you see in the movies. I mean, they seem totally different, right? But believe it or not, chemically, they're all related. They share a kind of secret identity.
And the answer is oxygen. Yep. All three are what we call organic compounds. But the thing that truly defines them, their family trait, is the oxygen atom and exactly how it's hooked up to everything else. It's really the heart of the whole family.
Okay, so let's get properly introduced to the three main members of this oxygen-centered family. You could say they all share a last name, but their first names and their chemical personalities are all based on really subtle differences in their structure. First up, the most famous member of the family, the alcohols. The key feature to look for here is the hydroxyl group. That's just an oxygen bonded to a hydrogen, or OH, and it's attached to a standard carbon chain, which chemists call an alkyl group. You can just think of this ROH formula as the classic family blueprint.
Next, we have the phenols. And here's where a tiny change makes a huge difference. Phenols have that exact same OH group, but, and this is the important part, instead of being on a simple chain, it's bonded directly to this super stable circular thing called a benzene ring. This makes it the sophisticated aromatic cousin of the family.
And finally, we have the ethers. Now, these guys kind of break the family mold. With ethers, the oxygen atom isn't hanging off the end as part of an OH group. Nope, it's sitting right in the middle, acting like a bridge connecting two carbon groups. Its formula, ROR', literally shows that oxygen linking two sides together. So now that we've met the whole family, let's zoom back in on the alcohols for a minute, because just saying something is an alcohol doesn't really tell you the whole story. We can get way more specific, and luckily, there's a really easy way to do it. We can classify pretty much any alcohol out there in two simple steps. First, we just count how many of those OH groups it has. And second, we look at the specific carbon atom that the group is actually attached to. Let's see how that works. So step one is basically a numbers game. If a molecule has just one OH group, like the ethanol in your drink, we call it monohydric. If it's got two, it's dihydric. And if it has three, like glycerol, which is used in soaps, it's trihydric. The more OH groups you add, the more its properties change. Now, for step two, it's all about location, location, location. We look at the exact carbon atom that's holding on to the OH group. If that carbon is only attached to one other carbon, it's a primary alcohol. If it's attached to two other carbons, it's secondary. And if it's bonded to three other carbons, you've got a tertiary alcohol. This is a perfect example of how structure dictates everything. Okay, so why do we care so much about that little OH group? Well, because it gives alcohols a chemical superpower, the ability to form something called hydrogen bonds. And this one single feature explains almost all of their unique physical properties. You could almost picture it here. The hydrogen on one alcohol's OH group is attracted to the oxygen on another one. They act like tiny little magnets, pulling the molecules together. And this strong attraction is called a hydrogen bond. And you know what else does this? Water. That's why smaller alcohols dissolve so easily in water. They just fit right in. And this superpower has a huge impact on boiling points. See, to boil a liquid, you have to break the connections between its molecules. For alcohols, that means you have to break all those strong hydrogen bonds, and that takes a lot of energy, which means a higher boiling point. Ethers, on the other hand, with that ROR structure, don't have a hydrogen on their oxygen, so they can't form these bonds. They're way easier to pull apart, and that means much lower boiling points. Now let's quickly check back in with our two other family members, the phenols and ethers, just to see how their unique structures really define them. Remember how phenols have their OH groups sitting on that special benzene ring? Well, it turns out that ring is so good at pulling on electrons that it actually weakens the bond between the oxygen and hydrogen just a little bit. This makes it easier for that hydrogen to pop off. And what's the definition of an acid? Releasing a hydrogen ion. So that ring gives phenols a completely different chemical personality. And ethers, well, they're all about that oxygen bridge. With no OH group, they can't do that powerful hydrogen bonding we talked about. This not only gives them lower boiling points, but it also generally makes them less reactive and more stable than their alcohol cousins. You could say they're the calm, steady members of the family.
All right, we've met the whole family. Let's put it all together in one final portrait to see them side by side.
So, here's the bottom line. For alcohols, having that -OH group on a carbon chain lets them form hydrogen bonds, which gives them higher boiling points. For phenols, putting that same -OH group on a benzene ring changes the game and makes the whole molecule slightly acidic. And for ethers, trapping the oxygen in the middle creates a stable bridge, which means no hydrogen bonding and a lower boiling point. 3 families, all defined by how they use one little oxygen atom.
And that really makes you think, doesn't it? It's pretty amazing how just moving 1 or 2 atoms around can completely change a molecule's identity and its job. It really leaves you wondering, what other massive changes in the world of chemistry are hiding in plain sight, just one tiny bond away? Thanks for tuning in.